You know, we're totally surrounded by incredible machines, the cars we drive, the planes we fly in, but what about the engines we can't see? Some of the most powerful machines on the entire planet are completely invisible, operating miles below our feet. So today, we're going to go deep underground and uncover one of these hidden technologies that brings critical resources to the surface.
All right, so to really get a grip on this technology, we first have to understand the basic problem it was built to solve. And it all boils down to one simple thing: pressure. See, when a new oil well is drilled, it's usually pretty easy. There's a ton of natural pressure in that underground reservoir, and it literally pushes oil and other fluids right up to the surface. We call those flowing wells. But that natural pressure, well, it doesn't last forever. Over time, it fades, and when it drops too low, the well just stops flowing. It becomes what the industry calls a dead well. And that is exactly where artificial lift comes into the picture. Honestly, you can think of it like life support for an oil well. It's the catch-all term for any technology we use to give that well the extra kick it needs to keep producing after its natural energy is gone. Now, there are a bunch of ways to do this, but we're going to focus on one of the most powerful and common methods out there, an amazing piece of engineering called the Electrical Submersible Pump, or ESP for short. And this is not some newfangled invention. The history here goes back over 100 years. It was pioneered by a Russian inventor, Armes Arutinov, who figured out how to build the very first electric motor that could actually work while being completely submerged in an oil well. He brought that idea over to the United States in the 1920s and founded a company that eventually became Rita, a name that, trust me, is still a giant in this field today. So, what does one of these things even look like? Let's break it down and build an ESP starting from the components that are sitting thousands of feet underground. Way down in the well, the ESP is this long, skinny assembly of 3 key parts, all stacked together. Right at the bottom, you've got the motor, which is the powerhouse of the whole operation. Sitting on top of that is the protector, or seal. Its job is absolutely critical. It keeps the nasty well fluids out of the motor. And then at the very top, you have the pump itself. That's the part doing all the heavy lifting. Now, here's where the design gets really, really smart. The pump isn't just one big propeller. No way. It's actually made of hundreds of tiny individual spinning stages, all stacked one on top of the other. Each little stage only adds a little bit of pressure, but when you stack hundreds of them together, whoa, their combined force is just immense, more than enough to shove thousands of barrels of fluid up a pipe that's several miles long. Of course, a machine buried miles underground still needs power and a way to be controlled, right? Well, that all comes from the surface. It's delivered through a specially armored power cable that runs all the way down the well. And that cable connects our downhole pump to the brains of the operation, which is sitting right up top. Back on solid ground, you've got the support gear. There's a switchboard, which is basically the control center. It monitors everything and protects the system from stuff like power surges. And then you have transformers. Their job is to take whatever power is available on site and tweak the voltage so it's exactly what that downhole motor needs to run perfectly. Okay, so we've built the machine. Now let's talk about the absolutely brutal world it has to live in and day out. It is not a friendly place. The world 2 miles underground is, well, it's a gauntlet of things trying to destroy this pump. You've got free gas that gets in and causes the pump to gas lock, where it just spins and doesn't move any liquid. You've got scorching hot temperatures that can literally cook the electrical insulation, corrosive fluids that eat away at the metal, and tiny bits of sand that act like sandpaper on everything. And to give you an idea of how serious that sand problem is, just look at this. The sand you find in these wells is mostly quartz. On the Mohs hardness scale, it's a 7. The super tough tool steel used to make the pump, that's about a 6.5. Yeah, that means the sand flowing through the pump is literally harder than the pump itself. It is constantly being sandblasted from the inside out. And then there's the heat, 250 degrees Fahrenheit. That's pretty much the upper limit for a standard ESP. If a well is hotter than that, you have to start using really specialized and much more expensive parts. The insulation on the motor, the seals, and the protector, they all have to be upgraded to advanced materials just to survive. So the takeaway here is that with all these things trying to kill it, failures are gonna happen. It's inevitable. And as this quote says, the electrical system is often the first thing to go. It's the weakest link. Which of course brings up a really big question. How on earth do you diagnose an electrical problem on a machine that's 2 miles straight down? I mean, you can't just send a mechanic down there, right? So instead, operators have come up with this really ingenious way to figure out what's wrong remotely.
They use the electricity flowing down that power cable as their eyes and ears. It's done with a tool called a recording ammeter. It's usually sitting in the control panel on the surface, and all it does is constantly measure the electrical current that the motor is pulling, and it records that measurement on a paper chart. This chart, it basically becomes the pump's EKG. It's a continuous heartbeat that tells you a very detailed story about what's happening miles below. And this is just a perfect example of how powerful that story can be. On the left, you see that smooth, steady line. That's a happy, healthy pump, working perfectly. But the chart on the right, that jagged, chaotic mess, that tells a completely different story. Those sharp spikes and dips mean the pump is fighting with gas. The current drops when it's just spinning in gas, and then it spikes when it finally grabs a slug of liquid. And different patterns can tell you about different problems. This one, for example, shows a pump that's just too big for the well. It sucks up all the available fluid really fast and then shuts itself off. But the timer is set too short, so it keeps trying to restart before the well has had time to refill, causing this repeating cycle of failure. So this whole diagnostic thing becomes a pretty simple 4-step loop. You monitor the current, you look at the chart for any weird patterns, you figure out what that pattern means, and then you take action. Maybe it's a simple tweak on the surface, or maybe it means you have to plan a major repair. But it's all done to keep that pump running for as long as humanly possible. When you step back and think about it, it's a truly incredible system. An ESP can take a well that was completely dead and turn it back into a money-making asset, all while surviving in one of the most hostile environments imaginable, right at the edge of what our materials can even handle. Right this second, there are thousands of these things running, miles under the ground all over the globe. They are these quiet, unseen engines, a testament to some brilliant engineering, and they're a huge part of the infrastructure that delivers the resources we all depend on every single day. And as we wrap this up, that kind of leaves us with a final thought. We just uncovered this one massive hidden machine that quietly keeps our world running. It really makes you stop and wonder, what other invisible engines are out there reliably powering our lives from just out of sight?